Right now, as you're watching this, trillions of tiny particles inside your body are doing something that should be impossible. They're passing straight through walls, not metaphorical walls, actual physical barriers that classical physics says nothing should be able to cross. And if they stop doing that, even for a second, the sun would go dark, your phone would die, and every atom in your body would collapse. That impossible thing has a name. And honestly, it might be the most important idea humanity has ever stumbled into. So let's start with a question. What's the most valuable piece of science ever discovered? You might think gravity, maybe evolution, possibly relativity. All brilliant answers. But here's the thing. There is one theory that is directly responsible for roughly a third of the entire global economy. One theory behind every single transistor in your phone, every laser, every MRI scan, every GPS signal, every LED light, every solar panel, and the flash memory in your USB drive. One theory that the entire $9.5 trillion semiconductor industry is built on top of. And most people have never actually had it properly explained to them. It's called quantum mechanics. And the story of how it was discovered is honestly one of the most dramatic, bizarre, and beautiful chapters in the history of science. Because quantum mechanics wasn't some elegant idea that dropped out of the sky fully formed. It was born out of desperation. It was hated by some of the greatest minds who created it. And it describes a universe so deeply strange that one of its own founders literally said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." That was Niels Bohr, and he meant it. So, let's go back to where this all began. And I promise you, by the end of this, you're going to see the world a little differently. It's the year 1900, the turn of the century. Physics is basically done. Or at least, that's what most physicists believed. Newton had given us gravity and motion. Maxwell had unified electricity and magnetism. The universe seemed like a giant clockwork machine, ticking along according to precise, predictable laws. Lord Kelvin reportedly said there was nothing new to discover in physics, only more precise measurements. And then everything fell apart. The problem was something called black body radiation. When you heat an object, it glows. Heat it more, it glows brighter. Classical physics had an equation for this, and that equation predicted that a hot object should emit infinite energy at short wavelengths. Infinite. Obviously, ovens do not emit infinite energy. Your toaster is not a weapon of mass destruction. Physicists called this the ultraviolet catastrophe, which sounds dramatic because it was. It meant their entire framework was broken. Enter Max Planck, a German physicist who, in 1900, did something radical. Not because he wanted to. He was actually quite conservative. But out of sheer mathematical desperation, he proposed that energy isn't emitted in a smooth, continuous stream, like water from a tap. Instead, it comes in tiny, discrete packets. He called them quanta. The singular is quantum. That's where the name comes from. Latin for how much. And his equation was beautiful in its simplicity. E equals h times nu. Energy equals Planck's constant times frequency. It solved the problem perfectly. The math worked. The ultraviolet catastrophe vanished. But here's the wild part. Planck didn't actually believe it. He thought it was just a mathematical trick, a temporary fix until someone found the real answer. He spent years trying to reconcile it with classical physics. He couldn't, because it wasn't a trick. It was the actual truth about reality. 5 years later, in 1905, a young patent clerk in Switzerland took Planck's idea and ran with it. Albert Einstein showed that light itself is quantized. It comes in little packets of energy called photons. This explained something called the photoelectric effect, where shining light on metal can knock electrons loose, but only if the light has a high enough frequency. It doesn't matter how bright a dim light is. If the frequency is too low, nothing happens. That only makes sense if light arrives in discrete chunks, not as a continuous wave. Einstein won the 1921 Nobel Prize for this. Not for relativity, for the photoelectric effect, for proving that light is made of particles. But wait, we already knew light was a wave. 200 years of experiments had proven that. So which is it, a wave or a particle? The answer is both, and neither. And this is where things get properly weird. In 1923, a French physicist named Louis de Broglie proposed something breathtaking. He said it's not just light that has this dual nature. Everything does. Every particle of matter is also a wave. You, me, a baseball, the earth, everything. We all have wavelengths. For a baseball, the wavelength is so impossibly tiny that you'd never notice. But for an electron, the wavelength matters enormously. De Broglie won the 1929 Nobel Prize for this. And he was right. So by the mid-1920s, physics was in chaos. The old rules were clearly broken. Energy comes in packets. Light is both a wave and a particle. Matter is also both a wave and a particle. And nobody had a proper framework to describe any of this. Then, in September of 1925, everything changed. Werner Heisenberg published a revolutionary paper in a German physics journal. He threw out the idea of electron orbits entirely and replaced them with something called matrix mechanics, a completely new mathematical language that described atoms using probability and uncertainty rather than precise trajectories. A year later, Erwin Schrödinger developed his own version, wave mechanics, with his famous Schrödinger equation. The two approaches looked completely different, but they turned out to be mathematically identical. Two roads to the same astonishing destination. And what did this new framework say? Something that still unsettles physicists today. It said that at the quantum level, nature is fundamentally random. Not random because we lack information. Random because randomness is built into the fabric of reality itself. A particle doesn't have a definite position until you measure it. Before measurement, it exists in all possible positions simultaneously. That's called superposition. And when you measure it, the superposition collapses into one definite outcome. But you cannot predict which one, only the probability. Einstein hated this. He famously wrote in a letter to Max Born, "God does not play dice with the universe." He spent the rest of his life trying to prove quantum mechanics was incomplete. He was convinced there must be hidden variables, secret information that would restore determinism. In 1935, he co-authored a paper with Podolsky and Rosen that challenged quantum mechanics using entanglement, this bizarre phenomenon where two particles become linked so that measuring one instantly determines the state of the other, no matter how far apart they are. Einstein called it spooky action at a distance. He meant it as a criticism. He thought it proved quantum mechanics must be wrong. It didn't. In 1964, a physicist named John Bell devised a mathematical test to settle the argument. And in 1982, Alain Aspect performed the experiments. Einstein was wrong. Entanglement is real. There are no hidden variables. Nature really is playing dice. Aspect won the 2022 Nobel Prize for proving it. Now here's where things get exciting, because you might be thinking, okay, that's fascinating, but esoteric, subatomic weirdness. What does this actually have to do with my life? Everything. Literally everything. In 1947, 3 physicists at Bell Labs named John Bardeen, Walter Brattain, and William Shockley invented the transistor. And the transistor only works because of quantum mechanics. The way electrons behave in semiconductors, the way they tunnel through barriers, the way their energy levels are quantized into bands, none of that can be explained by classical physics. Without quantum mechanics, there is no transistor. Without the transistor, there is no computer, no smartphone, no internet, no modern world. Your phone right now contains billions of transistors. In 2025 alone, over 1 trillion semiconductor chips were sold worldwide, at an average price of just 74 cents each. The global semiconductor industry generated roughly $600 billion in revenue that year, and it's approaching nearly $1 trillion in 2026. The combined market value of just the top 10 chip companies hit $9.5 trillion in late 2025. That's not just big. That's a significant fraction of all human economic activity. And every single dollar of it traces back to quantum mechanics. But it doesn't stop there. Lasers? Quantum mechanics. Einstein predicted the physics behind them in 1917. Theodore Maiman built the first one in 1960. Now lasers are in everything. LASIK eye surgery, fiber optic internet, barcode scanners, Blu-ray players, industrial cutting tools, military systems, scientific instruments, MRI machines that let doctors see inside your body without cutting you open. Those work because hydrogen atoms in your body have a quantum property called spin, and when you place them in a magnetic field, their quantum states can be manipulated to produce detailed images of your organs. GPS. The atomic clocks in GPS satellites depend on quantum transitions between energy levels. Without quantum corrections, your GPS position would drift by about 10 kilometers per day. Your phone would send you to the wrong city. Even your USB drive uses quantum tunneling. Electrons literally pass through an insulating barrier that classical physics says they cannot cross. That's how flash memory erases and rewrites data. Every time you save a file, quantum mechanics is doing something classically impossible. And here's a fact that might stop you in your tracks. Without quantum tunneling, the sun would not shine. The core of the sun is roughly 15 million degrees Celsius. That sounds insanely hot, but it's actually not hot enough for hydrogen nuclei to overcome their electrostatic repulsion and fuse. Classically, fusion shouldn't happen. But quantum tunneling allows those nuclei to pass through the energy barrier as if it isn't there. So the very light that keeps you alive, the warmth on your face, the energy that drives all life on Earth, is powered by particles doing something that should be impossible. Quantum mechanics isn't some abstract theory locked in a textbook. It's the reason you exist. And honestly, we're just getting started. Because right now, in 2026, which happens to be the United Nations International Year of Quantum Science and Technology, the second quantum revolution is unfolding in real time. And it's happening fast. Google's Willow quantum chip has demonstrated an algorithm running 13,000 times faster than a classical supercomputer. D-Wave achieved the first ever scalable on-chip cryogenic control for quantum computing in January. Fermilab and MIT Lincoln Laboratory successfully trapped and manipulated ions using in-vacuum cryoelectronics in February, opening a pathway to scaling quantum computers to millions of qubits. And just weeks ago, in late April 2026, researchers at Paderborn University and Sapienza University of Rome achieved quantum teleportation of a photon state between two completely independent quantum dots across 270 meters of open air at 82% fidelity. That's a crucial step toward building a quantum internet, a network where communications would be secured not by clever mathematics, but by the fundamental laws of physics, unhackable in principle by anything. Meanwhile, an Australian consortium is building a quantum-enabled brain on chip platform using diamond quantum sensors to measure real-time electrical activity from three-dimensional human neural tissues. Japan's National Institutes for Quantum Science and Technology published a defining paper in 2025 positioning quantum biosensors for earlier disease detection, faster drug development, and new routes to clean energy. And the fundamental physics keeps getting stranger and more wonderful. In April 2026, researchers at Tokyo University of Science observed wave-particle duality in positronium for the first time ever. Positronium is an exotic atom made of an electron and its antimatter twin, a positron. It literally annihilates itself in fractions of a microsecond. And yet they showed it diffracts through graphene just like a wave, proving that even matter-antimatter systems obey the rules of quantum mechanics. That opens the door to testing how antimatter responds to gravity, something nobody has ever directly measured. At CERN, the Large Hadron Collider discovered a brand new subatomic particle in March 2026. It's called GCC+, a baryon made of two charm quarks and a down quark, roughly 4 times heavier than a proton, detected at 7 sigma significance. That's the strongest statistical certainty in physics. And at Fermilab, the Microbune experiment used a 170-ton liquid argon detector and the work of 193 scientists across 40 institutions in 6 countries to rule out the sterile neutrino, a particle that had been hypothesized for 30 years with 95% certainty. Published in Nature. 30 years of theory, and the data said no. The mystery of the original neutrino anomaly remains, but now we know the answer isn't a hidden fourth flavor. Science doesn't just discover. Sometimes it undiscovers. And maybe the most poetic development of all. Researchers at the Indian Institute of Science found that electrons in ultra-clean graphene can flow as a nearly frictionless quantum liquid, violating a 170-year-old law of physics called the Wiedemann-Franz law by a factor of 200. That quantum fluid could one day enable sensors so sensitive they detect individual molecules or the faintest magnetic whispers from your brain. So here's what I want you to hold on to. Quantum mechanics started as a mathematical band-aid that its own creator didn't believe. It was fought against by the most famous physicist in history. It describes a reality where particles can be in 2 places at once, where measurement creates outcomes, where 2 entangled particles stay connected across the universe, and where things tunnel through barriers that should be impenetrable. It is the most precisely tested theory in all of science. The predictions of quantum electrodynamics match experimental results to better than 1 part in a billion. Nothing else in the history of human knowledge even comes close. And from that bizarre, counterintuitive foundation, we built the modern world. Computers, the internet, medical imaging, GPS, solar energy, lasers, LEDs, all of it. The phone you're watching this on is a quantum mechanical device, and the next wave, quantum computers, quantum medicine, quantum communication, is just beginning. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." And honestly, he was right. Even the greatest physicists in history have been humbled by it. But here's the beautiful thing. We don't have to fully understand it to let it transform our lives. We just have to keep asking questions, keep experimenting, keep being curious. Because if a desperate mathematical guess by a conservative German physicist in 1900 can lead, over 126 years later, to teleporting photons across buildings and discovering new particles inside atom smashers and building sensors that can watch a human brain think in real time, then honestly, the only limit on what comes next is how brave we're willing to be with the questions we ask. If this blew your mind, even a little, do me a favor and hit that subscribe button. Drop a comment telling me which part of quantum mechanics fascinates you the most, or which future technology you're most excited about. Share this with that one friend who loves science or who claims they don't, because I promise they'll love this too. And I'll see you in the next one.